Here are some general factors that affect acid strength. 1. To transfer protons, an acid must have the polarity shown there, which is to say that whatever H is bonded to must be more electronegative than the hydrogen. Ionic hydrides don't have this polarity. An ionic hydride is a metal bonded to hydrogen, and there are only certain metals that can do that, and the certain metals, just to remind you, are these, what I call the strong base cations. Those are the only ones that form hydrides. In other words, there's no such thing as, for example, aluminum hydride or iron hydride. Ionic hydrides don't have that polarity because it turns out that hydrogen is actually more electronegative than any of these 8 atoms. The hydrogen is not going to be donated for ionic hydrides. Carbon-hydrogen bonds don't have that polarity, and that's because they are essentially nonpolar. As polarity increases, acid strength generally increases. But if the HX bond is too strong, then the acid is weak. For example, hydrogen fluoride makes for a relatively strong bond, and a strong bond means that the H's are unlikely to pop off, which means we have a weak acid. And thirdly, stable, that is weak conjugate bases, like the nitrate ion and the chloride ion, tend to indicate a strong acid. And we recognize these conjugate bases as being the conjugates of strong acids. Let's tackle binary acids, which you recall are acids that contain hydrogen and one other element only. I've summarized the trend for binary acid strength here in the upper right corner. That's the first thing to know what happens to binary acid strength when hydrogen is combined with any of these elements. The binary acid strength increases going down and to the right. But let's talk in a little more detail. In a group, bond strength is the determining factor. As we go down a group, let's say hydrogen bonded to fluorine, then hydrogen bonded to chlorine, and hydrogen bonded to bromine, and hydrogen bonded to iodine, the charge separation increases because the atoms get bigger as you go down a group. And if the charge separation increases, the strength of the bond will be weaker because the charges are further apart, so the bond is weaker. Well, a weak bond makes for a stronger acid. Let's point out an example. Let's consider hydrosulfuric acid and hydroselenic acid. You can see that sulfur and selenium are in the same group. If we were to draw a representation of these molecules, you can see I've got the hydrogen atoms there, and then the selenium atom is bigger than the sulfur because it's got an extra layer of electrons. The distance between the centers of charge in H2S compared to H2SE, in H2SE the charge separation is greater, which means on the right these hydrogens are not held as tightly as these hydrogens here, which means that on the left the acid will be weaker. In other words, those hydrogens will tend to stay there, and on the right that acid would be stronger. Those H's are more likely to pop off because the bond is longer and weaker. In a period, bond polarity governs. So, as we go from left to right across a period, the bond polarity is going to increase and the acid strength increases. And we know this because as we go to the right, you're supposed to know that the electronegativity of the elements increases. For example, if we consider these two binary acids, which have oxygen and fluorine, of course, in the same period, there is a smaller electronegativity difference between H's and O's compared to H's and F's. And where there's a greater bond polarity, there's a greater acid strength. H2O, which can act as an acid, is a weaker acid than HF. Let's summarize. A good general rule for a substance to donate a proton is that the non-proton part of the molecule must be more electronegative than the proton. This is one reason protons, i.e. H pluses, don't pop off when bonded to carbon atoms. CH bonds are nonpolar. For binary acids, acid strength increases down and to the right. In a group, HX bond strength governs. In a period, HX bond polarity governs. See the diagram at right.